In the first part of this complex numbers video, I told you about these two forms in which you can write down complex numbers, and today I want to tell you one more, but it's important to focus on why was it a good idea to have two different ways to write them down. It's because the Cartesian form is interesting when you want to add complex numbers, and the polar form was interesting when you wanted to multiply complex numbers. And this is how that worked. When you multiply two complex numbers, you add their arguments, which are the angles of rotation of the two complex numbers. Now, I want you to just look at this sentence carefully for a minute, because we've seen something like this before. When you multiply two complex numbers, you have to add their arguments. Try to remember where you've seen this before. When you multiply two things, what you have to do is add their things. How can you fill in these blanks here in a different way than what was just written before? Pause the video if you want to give this a try. See if you can remember where you've seen this before. And this is the answer. When you multiply two powers of the same base, you add their exponents. It is the exact same sentence, but with different words in there. So this suggests to us that complex numbers can probably be written as a power where the argument is going to be the exponent. I'm calling this base just k right now. It's just a random letter that I picked, and I am going to calculate what the base needs to be in order for this to work. But first, let's remember that when you multiply two complex numbers, you add their angles, but you also multiply their radius, right? Because the complex number in general is not just cosine I sine of theta. It's also multiplied by r. So I have to put an r here as well. And this is going to work fine for multiplication, because if I have a different complex number to multiply by this z, then he also has a radius, which I'm calling p, and his argument is a different angle, alpha, but the base is the same letter k, okay? Because I'm talking about multiplying two powers of the same base. So if this is correct, if complex numbers can actually be expressed as a power of some base k that we're going to figure out later, then everything else works as it should, because when you multiply two of them, you are multiplying the radius, the r and the p, which is, like we were talking about in the first video, is two stretches, one after the other. So that's multiplication, that's working. And you're also adding the exponents of this base, which again is the adding of the angles of the two complex numbers. So let's go ahead and figure out if this works, then what should the value of the base k be? So I'm going to start just from there, the polar form of the complex numbers, without shortening it to cis theta. And I am going to write now the conjugate of that complex number. The conjugate is when we change the sign just of the imaginary part. And now I'm going to add those two lines together. Notice that the imaginary parts have canceled out. Now I'm just going to divide both sides of this equation by 2. And I'm going to look at the conjugate of the number z in the picture. So we are switching the sign of the imaginary part, which means that we reflect vertically, which is why the conjugate was a minus bi in Cartesian form, right? But if we want to look at it in polar form, it has the same radius, and the angle is also the same, but it's going down instead of going up, so it's going to be negative theta. And now that we are trying to write it as a power with the angle and the exponent, that's just going to be the negative theta in the exponent. And that's how I want to write this line now. It's z plus z star over 2, so it's going to be this plus this over 2. And now the r's are going to cancel out from both sides of this equation, right? I can divide both sides by r. That is already a very interesting expression for the cosine of theta. Let's put that aside. And now, instead of adding both lines, I'm going to subtract first line minus the second line. This time it's the real parts that have canceled out, cosine minus cosine, and the imaginary parts have added up, because this minus minus this is 2 of them. I'm going to do the same steps that I did to the other one. I'm going to divide the equation by 2. And once again, the conjugate has the same radius. It's the same angle, but with a negative sign. So I'm going to substitute these things into that expression. And at this point in the other one, what I did was divide both sides of this equation by r. But this time I want to divide it by ri. So the r's are going to cancel out, but there's going to be an I in the denominator here. So this is an interesting expression for the sine of an angle theta. It's even more interesting than the one for cosine because this one has a complex number right here. And I'm just going to look at both of them together. And now we're just going to have to use a lot of the things that we know about the sine and the cosine functions. They are periodic functions. I have put one period of each one here. The cosine is red, the sine is green. I have a whole other video about trigonometric functions, so I'm not going to go into much detail about any of these things right now, mostly because I'm not going to need that much of it. But you know, they look like waves. They have an amplitude of 1 unless you do a vertical stretch. You know, the sine and the cosine functions are a horizontal translation of each other. There's a very interesting fact that we know that if you take sine squared and cosine squared and you add them together, the result needs to be 1, right? That's the Pythagorean identity. And it's a fun exercise that if you do this to these two expressions, you square them and you add them together, they do add up to 1. It's a nice exercise. I recommend you go and do it. But that's not going to tell us what we want to know, which is the value of the base k. Because if you just do this exercise, you're squaring and adding, then things are going to cancel out in a way that it doesn't matter what value the base k has, and the thing just adds up to 1 like you want it to. So we're going to have to use something else. And we're going to use something that you may or may not know by now, depending on where you are in your studies of math. But the derivative of the sine function is the cosine function. This is true because the derivative of a function tells us the rate of change of the function at that point. So if you look at the sine function here, which is the green one, it starts by increasing, so it has a positive rate of change exactly where the cosine is positive. And then when the sine function reaches its maximum, it becomes horizontal at that point. It's not increasing or decreasing. That means that the rate of change at that point is 0. That's exactly the point where the cosine is 0. And then after that point, the sine function has a negative rate of change all the way up to here, which is exactly the part where the cosine function is negative. So it is negative because it is the rate of change of the other function, which is decreasing. These words that I've just said are obviously not a rigorous proof of the fact that the derivative of the sine function is the cosine function, but I'm just trying to convince you that at least it makes sense. And even though I'm not proving this, I am going to use it because it is true. So this is what I want to do. I want to take the derivative of the sine function, but written in this way, which we found up here. And then after I do that derivative, I want to compare it to the cosine of theta, which I know needs to be its derivative. So the first thing that I need here is the derivative of an exponential function of base k. Some people know this answer by heart. Other people like to think of it as a composite function with the exponential of base e and then applying the chain rule. But whichever way is your favorite, we're now going to have to do the same thing to the k to the power of minus theta, which now is going to use the chain rule to make another minus come over here. So that's going to be a minus with this minus is a plus. And the denominator is nothing because it's just a constant, so it just stays there as 2y. But the thing is that this needs to be equal to the cosine of theta, okay? So let's move this down here and compare. These two things need to be the same, so let's see what conclusions we get from that. Well, first of all, I can multiply both sides of the equation by 2. I think I'm going to split this fraction into 2 fractions, and I'm going to take the powers of k outside of the fractions. So here's what's happening. K to the power of theta is k to the power of theta times this thing, and the k to the minus theta is multiplied by the same factor. So in order for that left side to be equal to the right side, this factor needs to be equal to 1, because then I'm not multiplying either of the powers by anything. It's just k to the power of theta times 1 plus k to the negative theta times 1 again. So that's just that. And this fraction needs to be equal to 1. Remember, I wanted to figure out the value of k. So I'm going to start by multiplying both sides of this equation by I, and I'm just going to use the definition of log. K is equal to e to the power of I. This is the value that my constant k needs to have in order for this whole thing that I'm trying to do to be possible, in order for me to be able to write down a complex number as a power of a specific base. And remember, I wanted to do that because when I multiply two powers of the same base, I'm going to have to add their exponents, which is the angles of the complex numbers. And I already knew that when I multiply two complex numbers, I have to add their arguments, which is their angles. So then I have substituted the value of k that I found into my equations, and now I can do power of a power here, just so that it looks a little bit more pretty. And these two expressions are very well known, they are very pretty, and if you think about it, they provide an extremely interesting connection between two types of functions that you have studied before, but you thought they were completely different things. That's because when you were studying different types of functions before, you were thinking only in the real numbers. But when you put complex numbers into play, that provides a whole lot more structure to everything that is going on, to everything that the numbers are doing to each other. You used to think of the trigonometric functions as these two wavy things that I was showing you before. And an exponential function, e to the power of x, was something else entirely. It has the horizontal asymptote, and then it grows forever faster and faster. I have a whole other video about exponential functions in that sense as well. But now I'm telling you that these two functions are pretty much the same thing. They are pretty much the same thing in the sense that you can build one of them from the other and vice versa, if you allow yourself to think in terms of complex numbers. Now, when it comes to exam questions, knowing about this third way of writing down a complex number is not really going to change much in terms of what you're able to do to the questions and what the questions are able to ask of you, because you already knew to add arguments when you're multiplying two complex numbers, which is what's going to happen when you add exponents here. So the only thing that's really going to change is that it gives them new ways to write down the questions. It's almost just a notation thing. So now they can give you a complex number by saying this, and you're just supposed to understand that this means a complex number with radius r and angle theta. Okay, so let's do some questions. This one starts by giving us a number in this form and just asking us to write it in the other form. This is the kind of question that I don't like, that it's a show that, and it already gave us the answer. I feel like it's difficult for me to know whether the things that I'm writing down make it clear that I'm actually finding those numbers and not just copying from the answer that was given. But anyway, the real part of the number is -1, and the imaginary part is the square root of 3. So that is the number right there. And if I look at this right triangle here, the hypotenuse is going to be the radius, but this is 1 and this is √3. So I'm just going to do Pythagoras and find that r equals 2. Now, this is not a situation in which I would use Pythagoras normally, because when I see this triangle, I already know it. It's the triangle where the special angles are, like 30 degrees, 60 degrees. So I already knew that r was equals 2 when I did the picture, but I'm writing it very explicitly like this because of the show that issue. I feel like if I just wrote down r equals 2 the moment I drew the picture and realized it was 2, it would look like I was copying from this 2. But anyway, I know everything about this triangle, and this angle theta here, I know it's pi/6, but I'm going to write something else in order to show my work. So the sine of theta is the opposite leg divided by the hypotenuse, right? So I can say that is 1/2 right now. And then from that, I can say that theta is pi/6. Again, I'm not going to say 30 degrees because in this kind of context, it's always radians. But theta is not the argument of the complex number because the argument needs to be measured starting from the horizontal right side. So it's going to be pi/6 plus pi/2, and that is equal to 2 pi/3, which again was the angle that the question wanted. Now find the smallest positive integer n such that u to the power of n is a real number. So let's start from here. With n equals 1, u is clearly not a real number because it has that imaginary part. But if we go around another 2 pi/3 to get to u squared, that is still not a real number because now it's down here. But if I go around a third time to u to the power of 3, now it is a real number because I have gone around the circle one full time. So the answer to this question is n equals 3. That is not a lot of work for 3 marks. It makes us uneasy in terms of, am I showing my work well enough? But it's the picture, okay? If I was solving this question in an exam, I would have probably put this picture as my answer to part B, and not just use the first one that I used in part A. But yeah, this is enough to answer the question. Now the next item says find the value of un when n takes the value found in part B, which was 3. So u to the power of 3, what is going to happen? We already know that it's a real number, right? Because as for the arguments, we have added 2 pi over 3 plus 2 pi over 3 plus 2 pi over 3, which makes it an argument of 2 pi, which is the same as an argument of 0. But as for the radius, we have to multiply. So it's 2 times 2 times 2. That's 8. And now he comes back to that kind of question about roots of polynomials that I was doing in a different video. This is a polynomial of degree 3, so I know that it has 3 roots. I know that one of them is the u that was given, so I automatically know that another root, I'm going to call it v. It's the conjugate of that, because that's just a property of roots of polynomials, like I was mentioning in another video. And now for the third root, I am going to do the sum of all the 3 roots, which in this case is minus 5 divided by 1. So that needs to be minus 5. When I add u plus v that I already have, the imaginary parts cancel out, so that's just minus 2. So the third root needs to be negative 3. Negative 3 is a root that is easy enough that you can check if you're correct. So let's do it. Minus 3 to the power of 3, that's negative 27. Now that's 5 times 9, that is 45, minus 30 plus 12. I hope that is equal to 0. So here we have 15 plus 12, 27 minus 27. Yeah, that's equal to 0. Okay, next question. This one comes with a little picture. In the following Argand diagram, the points Z1, O, and Z2 are the vertices of a triangle described anti-clockwise. Well, that's because he went in this direction, so he's describing it anti-clockwise. It's a weird thing to say about a triangle. But anyway, let's continue reading. The point Z1 represents the complex number this, which is no new information here other than the fact that he wants to call this segment R1 because alpha was already the angle. I can see that in the picture. And the point Z2 is the same thing, but the angle is theta and the length is R2. Angles alpha and theta are measured anti-clockwise. Now, this is not a weird thing to say because now he is talking about how to measure angles in the Argand diagram, which is not surprising. This is the way we always measure these angles, and he didn't even need to say that. He also says that they are both in the first going around of the circle, but not necessarily in the first quadrant like the picture shows me. I'm not sure if I'm going to need that later. But he does say that the difference between them is between 0 and pi. So this angle that is inside of the triangle is an angle less than pi. Come to think of it, that's also obvious. It wouldn't be a triangle if an angle was bigger than pi. But he's just being extra careful and telling us a lot of stuff. Now part A, show that. A very weird equality. So what he wants me to do is to work with Z1 times Z2 conjugate, right? So Z1, I'm just going to put what it is because it says right here. And as for the conjugate of Z2, I am going to put the same thing that he said here, but with a negative sign in the theta because that's what the conjugate does. Instead of going up, it goes down, so the argument is negative. So times R2 e to the power of minus I theta. Then when I multiply these numbers together, I get e to the I alpha minus I theta, which then is the thing that he wanted it to be. That was a very simple show that question. Let's see what he wants next. Given that the real part of this number that we just found is 0, then show that something. But first, let's see what it means that this real part is 0. If the real part is 0, it means that the number is on the imaginary axis. It isn't the vertical axis. Now, for the range of numbers that alpha minus theta can be, the only number that does that is pi over 2. So I know that alpha minus theta is equal to pi over 2. This kind of thing is something that we were discussing in other questions in the part 1 of the video, right? When the real part is 0, the number needs to be vertical, so the angles need to be pi over 2 or 3 pi over 2 and so on. But in this case, it's only pi over 2. And again, I'm not liking this question very much because when I say that alpha minus theta is equal to pi over 2, then it's already obvious that the triangle has a right angle because alpha minus theta is this thing here. So if this is pi over 2, then yeah, that's a right triangle. So in terms of getting the 2 marks, I'm not sure it's clear when I write that I said it because of that and not because of the answer. So I guess this is one of those cases where, for lack of knowing what else to do, I would just literally write down what I was thinking. That's a sentence. Okay, so now he wants us to do something completely different. In part C, D, and E, consider the case where it is an equilateral triangle. So we're not going to use this pi over 2 anymore. Now we're going to use a pi over 3 instead. Express Z1 in terms of Z2. So if it is an equilateral triangle, the two radius need to be the same. This other side is the same number as well, but that's not important right now. And this angle here, alpha minus theta, is the angle pi over 3, or 60 degrees. So what has happened from Z2 to Z1 is that I've rotated by pi over 3, didn't do anything to the radius. So Z1 is the Z2 that has just been rotated by an angle of pi over 3. And how do we rotate? We multiply by a complex number. In this case, a complex number with radius 1, but the argument is pi over 3. And now he wants me to show another strange equality. I am going to start by just plugging things in, because he did say hence, right? And when he does that, it's usually continue to do something right after what you just did, which was that. So I'm going to take the z1 and square it, but it's going to be this z1 here, and then plus z2 squared. Now I know that I eventually want that to be equal to z1 times z2, because that's a show that. I can't write that down now because then I would be using the right side of the equation, and that's not how you structure a show that. But I know that that's the case, so I'm going to factor out a z2 from here. And I also know that I want a z1 to appear on that side, so I'm going to change that into this. I'm using the same equality again, okay? But now there were 2 pi over 3 here, so one of them I used to rotate the z2 and turn it into a z1, but the second one is still there. And I'm going to draw a picture. Look, I have z2, and then I rotated it 60 degrees, and I got z1. And I'm going to rotate it another 60 degrees, and I'm going to get this guy. I'm going to call him z3, okay? And then to z3, I'm going to add z2. z2 is this guy, so he goes in that direction. This is only working very pretty like this because the triangle is equilateral. So this guy here is z3 plus z2, which, if you think about it, is exactly what we wanted. And that's it. That's all I wanted to show you about complex numbers. As with every other topic, there can be easy questions and there can be difficult questions. You can't say that complex numbers is a difficult topic just because you thought this question was difficult. This was question 12 in a paper 1 a couple of years back. It's the last question in an exam. It's meant to be a difficult question no matter what it's about. And in this case, it was about complex numbers. But we've also seen some very easy questions about complex numbers, particularly in the first part of the video. So that happens with everything. But what I wanted to say is that even the difficult questions, like this one that we've just done, they become less difficult if you think geometrically. And now this is specific to complex numbers, but I don't even want to think about how I would have finished this last question without drawing a picture and without realizing that equilateral triangles, they make this pattern where the lines go like this and this and this, and you triangulate the whole thing. So that would be my suggestion, to make difficult complex numbers questions a little bit easier. Remember to think geometrically, and this is not something that you're going to be able to do if you do it for the first time ever when you run into a difficult question that you don't know how to solve otherwise. It's a skill that you need to train. So I would strongly recommend that you practice thinking about these things geometrically, even in the easy questions. Just because the easy ones you're kind of able to do blindly algebraically, that doesn't mean that you're getting all the training that you need in order to handle something more difficult if it happens to come up in an exam.